Now we're going to be talking about fluid dynamics, but in particular, pulsatile flow and turbulence. Pulsatile flow is what is caused by heartbeats. We're going to do the mathematics of what's going on in the blood, in our arteries and veins during a heartbeat. So that's important stuff. We move on. So during the heartbeat, the flow of the blood isn't continuous. So far, what we've been talking about when we use Bernoulli's equation or PHYS law is constant flow. We're never talking about flow that's starting or stopping, tapering off. Okay, it's just constant, right? So like you turn on a faucet and it's just flowing. What we're talking about here is different. During a heartbeat, the flow isn't constant. It's going back and forth, actually. So here in this picture, look, let's say this is a cross-section of a vein or artery. And during the heartbeat, a section of actually all of the blood will start moving forward and backwards, and it sort of jiggles, but with a marching in the forward direction. So if we were looking at a little volume of blood in a vein or artery, it could follow a path that looks like this. Look, beep, beep. That'll be one. Beep, beep. Okay, that's what you would be. That's what causes the heartbeat is like. You hear that beep, 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 beep. Okay, so those are heartbeats, are supposed to be. And so you watch, that's the big pulse, a little blip. Big, small. Okay, and you can see that there's a little bit of a back and forth action with the small part of the beat. Okay, so if we were to plot this flow rate versus time, the graph might look like this. In fact, they always look very much like this. There's a classic pattern to heartbeats. Whether you're looking at a human or a mouse, you're going to have a heartbeat that has this shape. So understanding and interpreting a graph of this sort is what medical practitioners have to do when they're understanding whether you have a healthy heart or not. So in this graph, you don't have to watch this graph for the whole day. What you do is you just have to look at a portion, okay, during one beat. So these graphs will typically have time that goes from 0 to, well, 1 beat. There'll be a little extra complication, but I'll tell you later, okay? So the next thing that's important in the graph is the vertical axis, which will be the flow rate, and typically measured centimeters cubed per second. So this is the graph we're going to try to quantify. We're going to try to analyze in a quantified way. Well, what are we going to try to get out of it? Well, I'll tell you. First, we're going to take the most important points on this graph. There's going to be Q max. That's going to be this point over here at the very top. That's going to be a very important point. The next thing is in the x-axis or the time axis, you're going to have these points in which the curve crosses the 0 line, okay? And so what we see is we're going to have two, this is positive direction, positive flow. And here, we're going to have negative flow, okay? So we've got two parts of the beat that have positive flow, and then we've got one part that's got the negative flow. So you could take down the points in time, we can call it T1, T2, T3, T4, and we can start analyzing this. So the main goal in analyzing a curve like this is to figure out what is the amount of flow, the volume flow of blood in one beat. Whether that beat's happening in half a second or a second or whatever, okay? What we want to know is how much flow, like is it a centimeter cubed? What is it per beat? So how are we going to figure out from this graph? What we need to do is the volume is going to be equal to the sum of those areas. And since the second area of the second curve is negative, okay, it's this formula here at the bottom. Volume is going to be equal to the area 1 minus area 2 plus area 3. That's how we're going to figure it out. Next, we're going to have to figure out what are those areas, those 3 areas. What we're going to do is we're going to make an approximation that, and it's a pretty good approximation, that these shapes are triangles. Okay, so area 1 is a triangle, area 2 and area 3 are triangles, they're all triangles. And we know that the area is equal to 1/2 the base times the height of a triangle. So all we need to do is measure the heights and the bases, multiply together, divide by 2, and you got your area of each triangle. The next observation that's made is very often area 2 and area 3 are equal and opposite. Okay, great. So they cancel. So if you can look at the graph and see that they are virtually the same, equal and opposite, okay, so one of them is just as negative as the other one is positive, they cancel each other out. And we don't even have to worry about it. So if everything works out, to be fortunate, all you need to do is figure out the area of that first triangle. And you're going to know how much volume flow you get per bead.